In this video, I'll show you how to solve the ALEKS problem called using the Arrhenius equation to calculate K at one temperature from K at another temperature. The form of the Arrhenius equation that we're going to use looks like this: natural log of one rate constant over the second rate constant is equal to E sub A, the activation energy, over R, the gas constant, times the initial temperature minus final temperature over the initial temperature times the final temperature. There are other versions of this. There are other ways to express this version of the Arrhenius equation, but no matter which form you're looking at, they can all be algebraically manipulated into this form right here. The value of R, this is our gas constant in the joules per mole form. So this is 8.3145 joules per mole Kelvin. And then because we're using kelvins in our constant, that means that our temperature needs to be expressed in Kelvin as well. So this problem is just going to be giving us a lot of data and asking us to solve for any one of these variables right here. Here we're being given the activation energy. Notice the units on the activation energy are joules, the units on units on the activation energy are kilojoules, and R's units are joules. So we're going to have to look out for that. We'll have to do a conversion there. The rate constant is telling us the rate constant is 23 when the temperature is 126 Celsius. So that means, and again, kind of the trickiest part of this problem is making sure that we're getting this data matched up. So we want to make sure, let's just call this rate constant our K1. So we'll call this temperature our T1. And then we're trying to figure out a different rate constant. We'll call that K2 at 54 degrees. We'll call that T2. And again, we want to make sure that we're really getting these numbers matched up correctly. We don't want to associate the wrong rate constant with the wrong temperature. So let's plug in what we have and do some unit conversions at the same time. Our rate constant K1 is 23. I'm going to leave the units off of it because they're just going to end up canceling out. That's going to be over K2, which we're trying to solve for. Our activation energy, 66 kilojoules per mole. Remember, we're going to have to do some sort of unit conversion here, and I find it easier to do that kilojoule to joule conversion instead of the other way around. So I'm going to go 66 times 10 to the third. That's going to get me converted into joules per mole over my rate constant, 8.3145. joules per mole Kelvin. And then my T1, 126, remember that's got to be converted into Kelvin. So that's 399 Kelvin minus T2, 54, which also has to be converted into Kelvin. So that's going to be 327 Kelvin. And then we want to divide that by 399 Kelvin times 327 Kelvin. A lot of math here. So I'm going to start by just trying to solve all of this on the right-hand side all at once. And actually, I said that I was going to leave units off, and then I started writing the units again. I'm going to go back and take my units off because there's just a lot of units here. It's just bulking everything up and giving us one more thing to worry about, and we can just kind of have faith that our units are going to work out. So I'm going to start with this portion of the equation right here. I'm going to emphasize that's multiplication. 399 minus 327 divided by 399 times 327. So this part of the equation right here is giving me 5.5 times 10 to the minus 4. And then I'm going to multiply that by 66 times 10 to the third and divide by 8.3145. This is giving me a result of 4.38. All of this together is 4.38, and that's equal to the natural log of 23 over K2. So now I've got to work on isolating this K2. What I'm going to do is use the inverse natural log to get rid of that natural log form, and that's going to mean that I need to take the right-hand side of the equation and use the E function right there. Now I'm going to do a little bit of algebra here. K2 times E to the 4.38 is equal to 23. And then I can just solve for K2. 23. Now, first I'm going to do the E to the 4.38. This gives me 79.9. And then I'm going to do 23 divided by that number. K2 is it wants 2 sig figs, so 0.29. ALEKS already has the units set up here. This is a pretty math heavy problem, so it's kind of a good idea to think a little bit about whether this number makes sense. The temperature has dropped quite a bit, which would be consistent with the reaction slowing down and the rate constant decreasing. So this looks like a pretty solid answer.